of frame relays.
Oh, that falls within ATM, just like any other packet switching or transmission switching services. You're gonna have challenges here and there. You're not gonna have a completely holistic, error-free or no issue or challenges uh, type of switching technology. There's always bound to be something, and usually it could be because of the way uh, uh, customer needs or user needs grow, and even cost as well could also be some of the key challenges that might affect a given type of switching technology. Okay, so to the brief introduction, back in the mid 1980s, there were three types of communication networks that had evolved. Um we had the telephone network that carries your voice calls, and then we had a television network that carries most of your video transmissions, and then a newly emerging computer network that carries data. So those were the three key communication networks that was evolving in the 80s. So hence there had to be a way of basically addressing the transmission needs that goes with some of these communication networks. The telephone companies realized that the voice communication was becoming a commodity service that had the profit margin uh, uh, with profit margins that would decrease over time. So they had to figure a way to address that. Obviously, the telephone companies realized that if they didn't catch up with their technology, with their network in terms of how voice and data was catching up to them, it would be a huge profit margin being lost in the process if they didn't up the game to address some of these things. So they realized that data communication was increasing, and then they had to come up with a solution to address that. So in the process, the telecommunication industry decided to expand its business by developing networks that could carry traffic other than just voice. So basically, carry all the various traffic within a given uh, uh, a communication network without having to deal with issues that revolved with with the previous versions or with each specific one that we had, like the voice, sorry, the telephone network or the television networks, and then the your data networks. So it was just in a way we're basically addressing key issues with transmission need that was growing at level. Okay. Asynchronous transfer mode or ATM is in a way similar to packet switching using X.25. So in a way, it was like the X.25 and frame relay as well. So falling back on the previous two uh, installment of the packet switching evolution, like packet switching and frame relay, like packet switching and within frame relay transmission, ATM involves the transfer of data in discrete chunks and organized into fixed size packets called cells. So generally, within ATMs, packets, so we don't call them packets, we actually call them frames because they had a lot more incorporated into it. It was a lot more than just uh, packets. Packets by its design or its format was much more less in terms of the number of bits or space it occupies as compared to your ATM cells. Keep in mind, ATM cell was designed to address high capacity needs. So obviously, if you wanted to break the information into packets, which had a much smaller uh, format in terms of the size of bytes or bits allocated to it, we couldn't address the high capacity need. So instead, it was they had to come up with a better, not a different approach, a different kind of fixed, organized structure uh, that could handle discrete chunks of data but instead at a higher level, at the higher capacity or higher volume, and that's what they call the cells. Okay, so I went through with this. I went over some of the wide area network technologies, or what you call the packet switching network transmissions that we had. So we had that lab was more or less primitive in a way. It was the EXO 25 that basically defined, that sets the tone for what really became the beginning of packet switching networks evolution. And then, so I went over that. We went over frame relay, and now we are on the asynchronous transfer mode. Great. So the telephone network transmissions with LAN links. Within ATMs, we had switching transmission technologies, which also handle switching as well. And then when it comes to synchronous optical network, which is another version of the of ATMs, or the SON as it's called, so transmission technology, which handles synchronous transfer modes, or STMs, which we'll look at as uh, which we look at in terms of capacity transmission. So here are some of the wide area network technologies with bandwidth capacities, or evolutions of the packet switching technologies over the years, from dial-up all the way up to ATM, just to address capacity needs. At level 0, we had the dial-up, basically, like I said, it was 64 bits per second transmission. In the 90s, in the 80s and 90s, if you had dial-up, yeah, you had connectivity. You could address uh, basic transmission needs like accessing static web pages and what have you. But obviously, it didn't address high volume of graphic and resource intensive web resources. It just can address that. And that's where the switch from the various standards, various evolution came about. And then we have level 1. Level 1 adapted uh, the X.25 and then the frame relays. Okay, so if you had frame relays or X.25, you fall within either 0 or level 1 category. And for the within the various regions, transmission in terms of bandwidth was for North America at level 1, we had 1.5 meg per second, which is a typical T1. Within the Japan region, you had 1.4 as usual. And then at the IT, which is the International Telecommunication Union standard, you had, I mean, like I said earlier, we had about 2. We could measure about 2, because within a frame relay, you could get a maximum or even more. But averagely, it was 2.048 megabit per second. That was being gained from the frame relay uh, packet switching option that we had, or evolution that we had. Okay, and then from there we move on to higher specs of that. Level 2, we had 6 meg for the North Americans, another 6 meg for the Japan region, and then 8.4 meg for the IT region, the European regions or whatever, which are called the E1s and the E2s. Okay, the North American had the T1s, J1 for the Japan regions, and then the IT had the European region had the E1s and E2s. And for the E3s, which are more of the uh, more or less the higher grades or higher levels uh, of the packet switching evolution, you had 44, and that's where that's what we start experiencing, like what we call pure broadband services. But generally, broadband services were categorized under anything above, I think it was 2 meg or so. But today it's actually around 5 meg. Talk about real broadband service, it's around 5 meg. So you're talking about level 2 here, where we had 6 meg and up. But level 3 was 44 meg. This is where ATMs and the evolution of high capacity transmission were being developed. Okay, and then level 4 saw 139, which is where your STMs are come to play. Okay, level 5 for 400 meg per second. That was amazing. 500 range. You know, and then STMs actually start at around 50, 51 meg. But generally, when we talk about STM1 today, we are looking at 150 plus transmission. Um, so you have STM, which is around the optical level, so using fiber optic basically. They will consider STM1s, STM4, STM16, 64, 256. So look at the capacity range within some of those. You had a line rate of for STM1, you had 155 meg, payload carries 150 meg, and overheads were quite minimal, 5 meg. And then it just evolved over time. Sonnet more or less revolved around fiber optics. This is where fiber optic took up and carried to handle the high capacity needs that transmissions require today, basically. So yeah, it's some of the evolutions over the years in terms of how the wide area of network technologies with reference to packet switching techniques have come over the years. Okay. The key goals of ATM was to address universal service and create a support, obviously create a support for all users to make sure every single user or infrastructures or vendors had a platform that users can easily adapt to address their specific needs. So it was designed to support all users. Um, it also had a goal of creating a single unified infrastructure for all service needs, also providing service guarantees and also creating support for uh, low cost devices. So it didn't matter how much the device was. Uh, Once it conformed to the ATM standard, it was able to address uh, your high capacity needs or services. Uh, Issues that really uh, led to ATMs or high capacity transmission technology to be developed or to evolve. One was traffic integration, integration, where we have voice, video, and data traffic, multimedia demands for web traffic, voice messages, internet multicast transmission, and then video conference as well. More or less higher traffic integrations was one of the key issues that was driving uh, uh, changes within LAN implementation to address high capacity needs at the service level, at the users level. Okay. So as I mentioned, yeah, traffic was one of the key part. Traffic integration was one huge part of it. Quality of service, limiting jitters, which is blocking streams of data within the transmission, or buffering, avoiding some of these things. Usually when you are within the lower transmission or bandwidth connections, you notice that when you're streaming, videos or uh, constant bit streams of information, you realize some of them it buffers, it kind of stops and reloads for a given time before it gives you uh, the feed to a certain point or certain time. Those were considered jitters, and one of those things that needed to be addressed within transmission needs was somewhat with the quality of service as well. We want to make sure we guarantee a better quality of service where jitters were limited and blocking of streams or buffering were also minimized. And another issue that drove LANs to change to high capacity transmission needs was LAN interoperability. I need to figure a way to mention the word without rolling my tongue too much. Okay, and then you also had mobile and wireless nodes. Yeah, so LAN interoperability and mobile and wireless nodes were the key issues that drove LANs to change. So it's design in terms of configuration for an ATM LAN. We had this design over here, this image over here that showcase the uh, the LAN design or its configuration setup. So within a typical example of a LAN setup or an ATM LAN setup, you'd have a terminal that connects to uh, an Ethernet switch, and then the Ethernet switch will probably have a higher bandwidth transmission to an ATM LAN network where you have high capacity needs being looked at. So you have your end devices or your terminals connect to an Ethernet switch, and that connects to your ATM networks. And that's where you have your high capacity needs flowing. So within two ATMs, you have 622 megabits per second. More or less, ATM came to address high capacity needs, So obviously, you'd have high transmission bandwidth within its LAN itself, within its LAN anyways. The basic ATM cell format, let's look at that very quickly. Uh, uh, yeah, let's look at that very closely. So we look at what makes an ATM a desirable uh, uh, transmission need for high capacity services. Okay, because obviously the format is the key. This is what's going to tell you how the the design really works to address high capacity. So ATM technology is a form of a virtual packet switching network that divides all data into small fixed size packets. That's called cells. They happen to be a connection-oriented service. Since it happens to fall under a virtual packet switching, it has to be connection-oriented, which reminds me, pointed out within the circuit switching, you say circuit switching is a connection-oriented service because it requires a dedicated path for continuous uh, data transmission. And it has to be in place before any kind of information can be transmitted over it. So hence they say it's a connection-oriented service. So the same applies to ATMs. They also happens to be connection-oriented services, and so would apply to your virtual circuit packet switching or virtual packet switching transmissions. Okay. Each ATM cell contains about 53 octets, which is 53 times 8. Okay, within its format. 5 octets, which is 5 times 8, it's about 40, right? 5 8 is what, 40, right? Yeah, for the which carries the header messages. So that chunk alone, that number of bits alone was allocated for just the header information. That's a lot. 40 bits for header information, or 5 octets. And a bigger chunk, what really makes it a high capacity transmission technology was the fact that they allocated 48 octets, so 48 times 8, for the actual data being transmitted. For the actual data actually being transmitted. Um, so here you do have the format, you have the header and the payloads. That kind of reminds me of a space shuttle, where the passengers actually sit in the header, and then whatever equipment that's been carried to outer space, to the International Space Station or this, are usually stored within the payload, and usually that's a bigger chunk of the shuttle itself, designed to carry huge capacity of equipment that needs to go up to the International Space Station. Okay, so you can relate it to what an ATM format is. You have the header that carries the 5 bytes, and then the or octet, 5 octets, and then 48 bytes of 48 octets for the payload. Good. In terms of conceptual model, ATMs usually organized in a hierarchy to make it much more efficient in its transmissions, or to address its specific goals and needs. Um, we have the users equipment. Actually, user equipment actually connects or uses equipment connects to a network, connects to an ATM network by an interface called the user network interface. So, which means if you're a subscriber and you subscribe for an ATM service, the installation is going to be done in this hierarchical order, where the user, your equipment would connect to the ATM network via a user network interface. And usually when you have that connection created, it's or established, you create what you call a permanent virtual channel, or PVC, for communication. Okay, connections between uh, provider networks are made through the network to network interface. So which means if you have two or more ATM networks that actually want to interconnect to share resources and provide wider coverage services or capacity needs or resource needs to service providers, to sort of users, then they will connect their devices at the network to network interface level. And that's where the ATM switch comes into place. Now, when that is usually established, or that connection is established, you create what you call a switched virtual channel, or an SVC, for communication. So for users, you connect to an ATM network via the user network interface, creating your PVC, or your permanent virtual circuit. And then for ATMs, or ATM devices that want to interconnect, like say an ISP runs an ATM network and wants to connect to another ISP that has got an ATM network, or an organization that runs an ATM network wants to connect to another organization that has got an ATM network, then they will actually talk using their network to network interfaces, or the ATM switches will connect via their network to network interfaces, and the process creates what you call a switched virtual channel for any kind of communication that they need. So this establishes the connection-oriented channel before cells are usually sent. So in the process of establishing some of these PVCs and SVC, you basically enable or you establish the connection-oriented channel for before any cell can be sent across the transmission. So here's a typical ATM network, what it looks like. So here you have a user or terminal connecting to an ATM network, which happens to be a private ATM network. So they obviously have to use the user network interface to connect to the ATM network. And then you have other ATM networks that are within the given ATM network that are trying to interconnect, or that are interconnected via the network to network interfaces. So this is actually a private ATM network that wants to communicate with a public. So you have a private and a public ATM network. And in this scenario, since you have different entities in terms of it's not a private to private or a public to public, it's a private to public. So the connectivity also revolves around using your user network interfaces, just like what you'd have for a private terminal. So the key thing to keep in mind within the ATM cell itself or LAN itself, it's all interconnected via the network to network. External connectivities, either from a terminal or from a separate type of ATM network, in this case a private and a public, would actually also connect using a public user interface or user network interface. Now, connections of ATM within ATM networks are very critical to defining uh, the way ATM actually switches cells within its devices, within its LAN or its implementation. ATMs do have what you call logical connections, and those logical connections are made up of virtual channel connections, or VCC, and generally a VCC happens to be the main logical connection within an ATM, and comparatively, it is somewhat related to virtual circuits within the the X.25 standard, which we mentioned earlier on within the evolution of packet switching. And then that usually forms the basic unit for switching within an ATM network. So generally, ATM networks implementations in terms of its connectivity, uh, we have two levels. We have the virtual path connection and the virtual channel connections, and those are termed the logical connection that we have within ATMs. The virtual channel connection, which is your VCC, uh, is generally uh, considered the main logical connection of an ATM, which is basically used or which is basically considered a unit for which switching is usually done with an ATM network. A VCC logical connection between two end users enables transmission for users to connect to an ATM network, or what you term a user to network exchange, for signaling control and what have you. So generally, VCC creates that user to network transmission. So in the case of where you had uh, an ATM network, a terminal trying to connect to an ATM network, the user network interface will probably have a VCC that creates uh, the signaling control mechanism to exchange information from the user point to the ATM network. Okay. So yeah, so the VCC generally creates connection between two end users to enable transmission for user to network exchange, and that usually relates to signaling controls for the most part. That's where your signalings are determined and how they are allowed into the ATM network from the user angle into the uh, network angle as well. And and also the network to network exchange for network management and routing of cells. Okay, so obviously you do have two key specific purpose that the logical connection uh, for the VCC, for the virtual channel connection, to play within the transmission. So one for allow for signaling controls at the user to network exchange of information, and then from network to network exchange for network management and routing of cells. Okay, so that's where you have the so if you were to go back here at this level here, you'd have what your network to network interface or exchange informations. And it's all handled at the VC